Okay, let's continue where we left off. So let's talk about conditional distributions. And conditional distributions are analogous to the conditional probabilities that we dealt with in chapter 2. And so we have let x and y be two random variables, discrete or continuous, doesn't matter. The conditional distribution of the random variable y, given that x is equal to little x, is given by f of y given x. Now, what here we have to notice that this given x, we're representing a particular value of x, a particular fixed value of x that doesn't change. So we have equal to f of x comma y divided by g of x. Okay. Again, the x's don't change, but y could vary. Okay. G of x is our marginal distribution that we had before, provided that g of x is greater than 0. This is similar to what we had before, where f of x, y represents our probability that x and y occur together. So that's x and y occur, divided by g of x, so just the probability that x occurred. Okay. And we have similarly the conditional distribution f of x given y. Here we fix the value of y, so it's constant. It's given by f of x comma y divided by h of y, where h of y is the marginal distribution of y. Okay, and this is very analogous to what we dealt with before with the probability of A given B, right? That's equal to the probability of A intersect B divided by the probability of B. Okay, so if you look at this probability A intersect B, those probability A and B occurring together, this is our joint f of x comma y. The probability of B, okay, probability of B is going to be given by these distributions at the bottom, either when we're dealing with the x values or when we're dealing with the y values. Okay, and I'm going to actually erase this in just a second. So if you're trying to write this down, I'm going to erase it. 1, 2, 3, it's going away because I need this space. I'll keep these up there for right now. Let's look at an example that I'm going to talk about independence. The easy example to do is with a discrete distribution. So here's example 3.49. Okay, 3.49. And we'll call it the control example. Okay. It says, let x denote the number of times a certain numerical control machine will malfunction. I apologize. It's the tornado warning that goes off on Wednesdays. Let x denote the number of times a certain numerical control machine will malfunction, 1, 2, or 3 times or on any given day. Let y denote the number of times a technician is called on an emergency call. Their joint probability distribution is given by, and I'm going to write this down. X goes from 1, 2, and 3. Okay. Y goes from 1, 3, and 5. That's Y. And I have probabilities of 0.05, 0.05, just going across, reading across the table here, 0.1, 0.05, okay, 0.1, 0.35, 0, 0.2, 0.1. And it wants us to calculate the marginal distributions of x and y first. I'm going to be a little bit lazier, and I'm not going to do the full marginal distribution like I did before. I'm just going to put them in the margins. So I'm going to make a totals call. Okay, a total. I don't have to have totals. So I get 0.2, 0. What's that? 0.5, I believe, and 0.3. That adds up to 1 on that side. Good. 0.1. This is 0.35. Okay, and this is 0.55, and that adds up to 1 as well. Good. So these are our marginals. Just to make sure that you remember, because it's kind of hard to, sometimes easy to forget. This is going to be g of x. And this is h of y. Okay. Very good. And so that answers A and B. Just to keep some space here. C says find the probability that y is equal to 3 given that x is equal to 2. So probability y is equal to 3 given x is equal to 2. Now we can solve this problem. We can solve this problem without using what we've learned about conditional distribution. I can say that this is just the probability of y equal 3 and x equal 2 divided by probability x equal 2. But let's just write it out in the way that we have it above. So this is the same thing as f of 2, 3, okay, 3. This 2 is a fixed value, right, because it could change over time. Of course, the 3 is fixed in this situation too. It doesn't vary. But the 2 is going to be a fixed value, okay? And that 2 we're going to plug into our marginal at the bottom, so g of 2. So f of 2, 3, when we plug the f of 2, 3 is, let's look at this. F of 2, 3 is 0.1, okay? And g of 2 is going to be 0.35. So we get 0.1 over 0.35, okay? Or that's about 0.286. 0.286. Okay. So that was pretty straightforward. Not too bad, not too difficult when you're dealing with a discrete random variable. When you're dealing with a continuous one, it becomes a little bit more difficult. And we're going to look at some examples of that. But before we do, we need to talk about independence. Okay. Independence. And we can say that x and y are independent, are random variables. Okay. Are independent if f of xy is equal to g of xy times h of xy. Essentially, if our joint probability distribution is equal to the product of our marginal distributions, right? So this is what this is saying. Are our joint probabilities equal to the product of our marginal probabilities? Let's look and see if our previous example is independent. And what I'm going to do is I'm just going to look at one of the case situation where x is 1 and y is 1. So what happens when x is 1 and y is 1? So if I have f of 1, 1, f of 1, 1 is equal to, is that equal to g of 1 times h of 1? Okay. So this is where my x is 1 and my y is 1. Okay. So f of 1, 1, if you guys look at that, that's 0.05. G of 1 is 0.1. H of 1 is 0.2. And by the way, these guys are not equal to each other, right? This is going to be 0.05 equals 0.02. These guys are not equal. So that implies that X and Y are not independent. Not independent. Not independent. Okay. So before I continue with this, I need to clarify a couple of things. Suppose, for example, that f of 1 was equal to g of 1 times h of 1. Can I say that x and y are independent at that moment? The answer is no. What I would need to do is I would need to look at every single possible combination of x and y. So I would need to look at 1, 1, 1, 2, 1, 3, 3, 1, 3, 2, 3, 3, 5, 1, 5, 2, and 5, 3, and see if every single possible combination of those guys was equal when I look at their joint versus their product of their marginals. If even one of these guys was not equal, then I would have to say that X and Y are not independent. So I was very lucky that the first one I did, F of 1, 1, where X is 1 and Y is 1, those guys were not equal to each other. So I could automatically say that X and Y are not independent. But if every single possible combination of these X and Y's had that my joint was equal to my marginal distributions, the product of my marginal distributions, then I would say that X and Y are indeed independent. Okay, that's for the discrete case. For the continuous case, it's a little bit easier when I want to talk about independence. And we're going to look at an example of that right now. Let's look at example 3.56. It says a joint density function of the random variable x and y is given by, let's give this a name. We'll call it the independent example. Okay, independence example. And it says it's f of xy is 6x if x is between 0 and 1. Oh, but now we have this dependence relationship on y on x. And y, it's between 0 and 1 minus x. 0 otherwise. Okay. So let me draw the domain of my function here first. Okay. Well, we know that x is going between 0 and 1. Okay. However, y is between the functions y equals 0 right here, and the function y equal 1 minus x. Y equal 1 minus x, which is going to be the line. That's a terrible line. Okay, that's a little bit better. Just think that's a straight line. Y equal 1 minus x. Or I could write this as x equal 1 minus y. Right, just reversing, just switching, solving for x. Okay. So my region is this area right here of my function f of xy. Right, so we got to keep that in mind. So everything I'm doing, every probability I'm calculating is going to be within this region. Outside of this region, my function is 0. So I don't have to really think about it too much. So this is the only place where my function is above the x-axis, or actually above the xy plane, because we're in 3 dimensions now. Okay, very cool. So let's determine whether x and y are independent. It says show that x and y are not independent. So they're kind of giving away what we need to do in A. To do that, I need to calculate the marginal distributions. So let's find g of x first. Okay, I need to integrate over my region, over all of the y values. Okay, now we need to figure out what's the range of y. And the range of y is between, we've already said, between 0 and 1 minus x. Okay, so that's going to be my limits of integration. 0 to 1 minus x. Okay, 0 to 1 minus x are going to be my limits of integration. And when I do that, my answer that I obtain when I do this is 6x times 1 minus x. X is going to go from 0 to 1. So when you look at this, my range for y was from 0 to 1 minus x, right? Because y depends on x. And then my limits after this is from 0 to 1. Okay, 0 to 1, which is what we have here, 0 to 1. So I have 6x times 1 minus x, the quantity 1 minus x, x goes from 0 to 1. Now let's do h of y. To do h of y, I'm integrating over all of my x values. Okay, now I need to find my limits of integration for x. Now, some of you guys are saying the limits of integration for x should be from 0 to 1. However, remember that now that we're focusing on the y's, right? Y is going to be what we want to do. I got to be clear here, is that I need to figure out what are going to be the limits of x in relationship to y. So let's go back to our triangle. Okay, our triangle here. Another way that I could have wrote these same, I could have wrote limits for this triangle is I could reverse this relationship between x and y. I could say instead that y goes between 0 and 1, okay, which is true. And x is the one that's between 0 and 1 minus y. And that's indeed true, right? Y does go from 0 to 1. And x does go from 0 to this line, x equal 1 minus y. So I can draw another one here. Draw another. Let's do orange. Okay. Kind of reversing my thinking here. Okay. So I'm focusing on how is x restricted by y, right? To figure out what my bounds for my limits of integration are. And x is restricted by y. It cannot be any lower than 0. It cannot be any higher than y minus 1. Okay. If we solve this, we get, what do I have? 3 times the quantity 1 minus y, that's squared. Y goes from 0 to 1. Okay. So we have to be a little bit more careful when we do g of x and h of y, especially when we have a dependence relationship of x on y or y on x. Okay. But we're done. These are our answers. So yeah. And now the question is, does f of xy equal g of x times h of y? And the answer to that is an obvious no, right? We could say 6x definitely does not equal 6x times 1 minus x times 3 times 1 minus y squared. And even their domains are different. These guys are not the same at all. So we can say X and Y are not independent. Not independent. And then B says this. Well, before I go to B, you say, well, Dr. West, you show us two examples where they're not independent. Are we going to ever see an example where they are independent? And the answer is yes, we will. We're going to look at one of those after this example. But let's keep going. So what's the probability that X is greater than 0.3 given Y is equal to 0.5? And this probably is a better idea for me to go to a different sheet. So let me go to a different sheet to do this example. Probability X is greater than 0.3 given Y is equal to 0.5, right? So Y is a fixed value of 0.5. Okay. The first thing we need to do is we need to calculate the marginal, the conditional distribution. So f of X given Y, our Y in this case is going to be 0.5. Okay. Just keep that in mind. This is going to be equal to F of X comma 0.5 divided by G of 0.5. Okay. And we're going to actually have our limits of integration are also going to depend, because this is a function, because this conditional distribution depends also on what Y is, right? Our limits for our function also depend on. So our limits of our function are going to be from 0 to 1 minus Y, or 1 minus 0.5. These are my values here. And I'm going to go back and I'm going to talk about that in just a second. So let's keep going. So F of X given Y is equal to, let's plug in F of X comma 0.5. If you do that, you get, well, there's no Y's in my joint distribution. So I just have 6X. That's kind of nice. Divided by, oh, it's at G. It should not be G, right? I apologize. That should be instead of G, because we're dealing with Y at the bottom, that should be a H. Okay. H of 0.5. So my H is 3 times 1 minus Y, which is 0.5 squared. And X goes from 0 to 0.5. And that simplifies it just a little bit. So I get 2x. Okay, so 1/2 squared at the bottom, that becomes a 4 at the top. So 24 divided by 3 is 8. So I get 8x. X goes from 0 to 0.5. Okay. And now that we have this, before we, well, let's integrate this. So what's the probability? X is greater than 0.3 given Y is equal to 0.5. Well, that's going to be equal to the integral from 0.3 to my upper limit of X, which is 0.5 times 8x dx. And when you integrate this, you get 0.64. This is our answer. Now, let me talk a little bit more about this part here. Why do we have this limit from 0 to 0.5? And let's just go back to that triangle. Actually, I can just draw the triangle right here. So we had 1, 1. Then we had our line, right? So we have this, this. Okay. So this is my region, right, that we have for our function to exist in. And what we're saying is that we know y is 0.5. Okay, we know y is 0. We have no doubt that y is 0.5. This is what this statement says. Y is equal to 0.5. So y is equal to 0.5. So how does that restrict the domain of x? What could x be in that case? So x can only go here, from here to here. Okay, this is my limit. What's that value going to be? That's going to be the value of 0.5. It can only go from 0 to 0.5. And that's where we get this bound from. Okay. And that's what we're seeing in our example, right? It's restricting our limit, okay? So that if we know that y is 0.5, then x cannot go any further than 0.5 itself in the xy plane. All right. That's it for that particular example. Let's do one more example and we're done for this week. I'm not going to do any more of these, I think, unless they have me in quarantine next week. Hopefully they won't. I'll be able to see you guys on Monday. But just in case this is going to be our last one, I need to get your test ready for Friday. So let's focus on one more example and then we'll be done and I'll give you guys some homework over this and hopefully you'll be able to do it. All right. So example 3.42. Let x and y denote the lengths of life in years of two components in an electronic system. If the joint density function of these variables is, let's give it a name, life example. Okay. Okay, life example. And I have the function f of x, comma y is equal to, here I have e to the negative x minus y. X is greater than 0 and y is greater than 0. Okay, so x and y are both greater than 0 and 0 elsewhere. Again, like I said, my handwriting is too bad. Just look at the PowerPoints. And I know I wrote the e to the, I think they have e to the negative, the quantity x plus y. I just distributed the negative through to make life a little bit easier. So we want to find the probability that x is between 0 and 1, given that y is equal to 2. Before I do that, I'm going to actually show that x and y are independent random variables. To do that, we're going to need to figure out what g of x is. So g of x. And if we look at our region for this, this is where x and y are greater than 0. And that corresponds to everything in the first quadrant. Notice that there's no dependence relationship of x on y or vice versa. So that makes life a little bit easier. So when I find the marginal distribution of x, right, I just integrate over all the y. So that goes from 0 to infinity. E to the negative x minus y dy. And that gives me e to the negative x for x greater than 0. H of y, I do the same thing. I integrate over the x's. Goodness. I get e to the negative y, y greater than 0. And the question is f of xy equal to g of x times h of y? And indeed it is. E to the negative x minus y is equal to e to the negative x times e to the negative y. And definitely their domains, when you combine them, are also the same. Okay, so the answer is yes. X and y are independent. Okay, so let's answer the question. Find the probability that x is between 0 and 1 given that y is equal to 2. To be able to do that, I need to find a conditional distribution, f of x given y. My y in this case is equal to 2. My y in this case is equal to 2. So plugging in, I get f of x comma 2 divided by h of 2, because y is what I'm looking at. When I plug in, I get this. I get e to the negative x minus 2 divided by h of 2, which is e to the negative 2. And that gives me e to the negative x greater than 0. Right? There's no dependence relationship on of x on y or vice versa. So we don't have to worry about that. And notice that my conditional distribution is equal to my marginal distribution of x. So the f of x given y is equal to g of x. And if you guys remember, this is very similar to what we had before. When we have independence of events, the probability A given B is equal to the probability of A. And it's a very similar thing. So knowledge of y doesn't affect the value of x. Okay. So let's solve this problem. What's the probability that x is between 0 and 1 given y is equal to 2? Well, it's the same thing as the probability that x is between 0 and 1. So I can look at that from 0 to 1. Okay. E to the negative x dx. And that works out to be 0.6321. Okay. And that is our answer to that problem. Okay, I hope that makes sense, right? It looks a little bit like chicken scratch a little bit, but if you're following along with me, then you probably are able to understand what's going on a little bit. All right, I will talk to you guys later. I think this is going to be it for today. And you guys have a wonderful week.